this scenario. So this is t, and this is y, and we have a function, and this is f of t. And we have an interval, let's say a comma b, and we already know how this is calculated. Is the exact area between a and b, the integral from a to b, from f of t dt is the exact area under the graph. So bear with me. I want to write down two things before we continue. So the fundamental theorem of calculus part 2 did what? Taught us how to calculate definite integrals. Now, part 1 that I'm just trying to talk about here. Part 1 will show that differentiation and integration are inverse operations. What does that mean? When I integrate a derivative, these two will cancel out. And of course, when I cancel this, I cancel this. So this symbol without the x does not exist. So when I integrate a derivative, I get the function. When I integrate a function and then differentiate, I get the function. What does that mean? This operation and this operation cancel each other because they are inverses of each other, and I get the function. When I differentiate an integral, I get the function. When I integrate a derivative, I get the function. So part 1 will show this. You can say, when I finish showing part 1, you could say maybe that it's clear, or you could say, you know, it's in a kind of a roundabout way of showing it. It's possible. I will agree with that too. I'll try to make it as simple and as clear as possible. So part 1 will show that differentiation and integration are inverse operations, basically this. And part 2 taught us how to calculate a definite integral. That's why I couldn't wait till this section. I needed it earlier. Okay. Back to our graph. This is between a and b, so t is a number between a and b. But now I'm going to say x, some x, is between a and b as well. X could be this, or could be here, or could be here, or could be here, or could be here. Let's say I choose x to represent, to graph here. What will this represent? Can anyone tell us if this is x? What does this represent? And how do I write it?
The integral of x from a to x.
So the integral for excellent from a to x from, of course, it has to be from f of t dt. Great. Stay with me. Excellent. Who was that, Sean? Thank you. Great. So now we have this on our hands. The integral from a to x from f of t dt. Good. So what does this represent? This is not a number. So if this number, this x, is a, you will say you get 0. if this x is, let's say, 1, I don't know what a and b are, but let's say 1, then you will say the integral from a to 1 from f of t dt, of course, is another number. Then if x is 2, you will say the integral from a to 2 from f of t dt is another number. If x is 3, and I can continue forever. So then what am I really trying to do here? What is this then? If for every input I get a totally different answer, different output, what did I just create? I'm just going to plug my device in. What did I just create? What do you think this is? We've done that all the time since we first started, algebra, right? When I have an input and I get an output, and again I put another input and I get another output. I put another input and I get another output. What am I creating?
This is another function.
Awesome! This is it. It's a function of x. Exactly. So what am I looking at? This is a function of x given or presented in the form of an integral. In the form of an integral. We can calculate this. This is a function. There's nothing to calculate about. If you give me the x, I'll calculate the output. But this is a function. So the function is given in the form of an integral. Why? So we can illustrate this. That's why we are defining this function in the form of an integral, to illustrate that. So what am I going to do? I'm going to differentiate both sides of this to show that I'm getting that. That's the whole thing. Nothing else. So again, we cannot be asked to find the integral from a to x from f of t dt. No. We can only be asked to find, we are asked to find g prime of x. That's it. Okay, fine. Just to show that when I differentiate this side and I don't want to go there, I want to write it one more time. So we have this function, brilliant function, in the form of an integral. Fine. Now let's see what we get when we differentiate. What is this function all about? It's nothing else but f of x. Of course, g prime. That's all it means. So we are creating this function just to show that when we differentiate it, we get the function back. Notice a few things here. This must be a number. A number. Any number. It cannot be x or x squared or x cubed or tangent x. It has to be a number. The other thing is, notice that this, in the formula, in the fundamental theorem of calculus part 1, so this is FTC part 1. This is plain x. But what if it's not? Because it's plain x, I should have multiplied by x prime. But because it's plain x, this is 1. So there is no need. That's the inner function prime. But what if I have a function like this? From 3 to tangent x from the square root of 1 plus t dt. No one can ask me to do anything else but find g prime. There is no such thing. We are only asked to find g prime. Okay, so how do I find g prime for something like this? Very simple. G prime of x equals, I replace t, because I'm differentiating this side and I'm differentiating this side. This symbol goes away, this symbol goes away, and the square root becomes 1 plus tangent x, but this time this is not plain x, so I have to multiply by this function prime, which we know is secant squared x. This is it. Another example, what if I'm asked, what if these are reversed? So what if I'm given this function? Then I have to use one of the properties that we just discussed, which is this. Reverse the limits of integration from 3 to tangent x, the square root of 1 plus t dt. First, I have to do that first, because this must be a number. Mandatory. Otherwise, FTC part 1 does not work. And now I differentiate the left-hand side. I differentiate the right-hand side, and I know this symbol and this symbol, these two go away, so I have 1 plus tangent x times the inner function prime, secant squared x. And there is one other possibility, last one, in which both top and bottom limits are functions. That is not difficult, but is the most sophisticated one. So give me an example. Give me any function here, and any function here. Anything you want. Or we can choose from the book. Let's choose from the book if you don't want to. Okay. Right here. 67, 68, 69, 70, 71. You choose. Okay, I choose 69. Unless you want to change it, go ahead. Please, I just...
68?
68 is good. So we have, let me write 68. And 68 we have 1 minus 2x, 2, 1 plus 2x. And we have t sine t dt. Awesome. Perfect. Okay, very good. Well, I have some prep to do. Remember one of the properties of the definite integral from a to b? I can break it up anywhere I want. From 1 minus 2x to whatever you want. You don't even have to put anything, or put 0, or put whatever. A circle, a triangle, anything. Remember, I'm breaking it at the same point, of course. T sine t dt. And I have one more step. This is okay, but this is not. And then we can differentiate. Minus stop, full stop. So now I can differentiate. So let's take a look before we do that one more time. These were not, this one was not a number. Both are functions. So the integral from a to b is the integral from a to c plus the integral from c to b. This is one of the properties we talked about today. Also, FTC part 1 requires that this is a number, not this. So I have to reverse. That's another property we looked at today with minus in front. Now this is all set. I can differentiate g, and I differentiate this. Minus stays outside. T is now 1 minus 2x sine of 1 minus 2x times the inner function prime, which is negative 2, plus, I differentiate this now. It's t, which is 1 plus 2x, sine of 1 plus 2x times the inner function prime, which is 2. This is it. I would just rearrange a little bit and put minus 2 in front. So this is positive now. So 2, 1 minus 2x, sine 1 minus 2x, and 2 in front, plus 2, 1 plus 2x times sine 1 plus 2x. So in these situations, we can never be asked to do anything else but differentiate the function given in the form of an integral. Why? Just because we want to show that integration and differentiation are inverse operations. So every time I integrate a derivative, I get the function. When I differentiate an integral, I get the function. That's the only purpose. Well, there are other applications of functions that are given as in a form of an integral. There are other applications. I don't know why the color is so it's either too much light. I just hope that you can see well.